So today's topic is Gauss law. Okay, so I'll be starting with the electrostatic flux. Okay, so let's start with the electrostatic flux. So how we define electrostatic flux first of all? Okay, what the definition of the electrostatic flux? Wait a moment. So first of all, what is the definition of electrostatic flux? Simply, electrostatic flux, the closed surface. How it is defined? It is defined as the number of field lines, like this. It is defined as number of field lines, electric field lines, number of field lines passing through a closed surface. Number of field lines passing through a surface. Passing through a surface. So simply number of field lines that are passing through a surface, and it's defined as what it is defined as electrostatic flux. Fine. Okay. So first of all, what I will do is this: I will define the electrostatic flux, and we'll be doing some example of the electrostatic flux, and then we'll be going. Then we'll be starting with the Gauss law. Fine. Okay. So let me first of all define this flux, electrostatic flux, and let's do the example from that is there. Okay. To concentrate here. So electric flux simply defined as number of field lines that are passing through a surface. Okay. Then mathematically, how we define electrostatic flux? How we define electrostatic flux? For example, here we have, suppose that these are electrostatic field lines. This represents a uniform electric field. Okay. Equispaced parallel lines, they represent a uniform electric field, isn't it? Now here we have this an area vector like this. So for example, here we have this rectangular lamina like this. This rectangular lamina, and the area vector will be obviously in this direction. So this will be area vector. Okay, this area vector. Okay. Now you want to calculate what the flux. Obviously, the flux will be equal to what? That will be equal to, for this very case, this flux will be equal to E multiplied by A, simply the product of electrostatic field intensity multiplied by area of this. Fine. And area vector simply is the vector quantity whose magnitude is equal to the area of the rectangular sheet and whose direction is perpendicular. Okay. So E multiplied by A. But this is true only if this is true under two conditions. Number one is that if electrostatic field and area vector are parallel to each other. Electrostatic field is parallel to area vector, and number second is that the electrostatic field is uniform. Only then you can write down the flux is equal to what? That's equal to E multiplied by A. Number one. Number second equation, for example, suppose that we have this equation, that is the uniform electrostatic field. This is a uniform electrostatic field, and it's not necessary that the area vector will be what? It will be parallel to the electrostatic field. It can be like this as well. Now this can be the rectangular area like this. Okay, so the area vector is directly along this direction, and obviously electrostatic field is along this direction. Then the two are inclined to each other at an angle theta. For example, this angle is theta. Okay, then in this very case, the component of the area vector parallel to this will be equal to A cos theta. Along this direction, there will be a component of area which will be equal to A cos theta, which is parallel to the electrostatic field. So for this very case, so this is our case first. This is our case now first is the electrostatic field is number one, it's parallel to the area, and number second, it's uniform as well. And number second is that if, for example, electrostatic, so this case number second, if the electrostatic field is uniform but E and A they are not parallel. So this is a more generalized case. In this very case, the flux will be safely equal to E multiplied by A multiplied by cos theta. Or you can take the dot product, so you can write it like this: E dot A. It's equal to E dot A. Dot product of this electrostatic field and the area vector. Okay. Then there's situation number third. Situation number third is this. For example, if the electrostatic field is not uniform, if electrostatic field is not uniform, is non-uniform. Number one, in general, electrostatic field is non-uniform, and E and A they are not parallel to each other. E and A, that's electrostatic field and the area vector, they are not parallel to each other. Fine? So they are not parallel or non-parallel. So electrostatic field and this area vector, they are non-parallel. Fine? E and A are non-parallel. Okay, so rather they are inclined to each other at some angle, so they are non-parallel. Now in this very case, how to calculate electrostatic flux is this. So it's like this. For example, here we have this a non-uniform electric field represented by this in general. And for example, there's an area vector like this. For example, here we have this rectangular lamina. It's placed somewhere here. Okay, and this is the area vector. Okay. Now here we have electrostatic field. Okay, in general, electrostatic field and area vector is not parallel. And number second, the electrostatic field is not uniform. So in this very case, how to calculate the flux? This is the way. How to calculate flux is this the way. Okay, so how to calculate flux in this very case? This is the way to calculate flux. So first of all, I will calculate the flux through a small elemental area that will be equal to E dot dA. Dot product of electrostatic field and dA. And what is this dA? it's the elemental area here. Okay, I can take the elemental here this. So this is the elemental area which is equal to dA. Now the flux through this will be equal to E dot dA, because safely we can assume that for this very small area the electrostatic field stays constant, which implies that we can write out this d phi, which is the elemental flux, which is the incremental flux, and that's equal to E dot dA. And then if you want to calculate the net flux, the net flux will be obviously equal to what? That will be equal to integration of E dot dA, like this. It's rather surface integral of E dot d. So here I will write down it's surface integral of E dot d. Okay, so this is our equation number 2. So this is our equation number first. This is our equation number first. Then this one is the equation number second. This one, dot product of the two, this is the equation number second, and this is the equation number third. Okay, so equation number third is the more generalized equation, or rather in general we write down the flux like this: integration of E dot dA. If, for example, let's suppose that the electrostatic field is uniform. When it's uniform, what you can do is this: you can pull this electrostatic field out of this integral, then it will simply become E dot A. Integration of dA is simply equal to A, so it will become E dot A. Okay, so that in the first case, and the second case, they are simply the special cases of the case number third. The case number third is the more generalized equation. Then here we have an important point, and that important point is like this: for closed surface. If, for example, there is a closed surface, like for example there is a cuboid, or for example there is a sphere, or for example there is a cone, like that, for closed surface, this flux is really written like this. Flux is written like this: it's equal to integration of E dot dA. Simply this circle on this integral implies for a closed surface the flux is defined by this equation. So this is our equation number 4. Now the most important equation is the equation number 3 and the equation number 4 here. Okay, so this will give the flux for the open surface, and this will give the flux for the closed surface. Like for example, open surface implies, suppose there is square lamina, or there is this circular disc, or for example there is the rectangular lamina. So that's called open surface. Closed surface implies which is bounded surface, like for example there is sphere, or for example there is a cone, or for example there is cylinder, and so on. So those surfaces are called as closed surface. Okay, so I'm sure यहाँ तक आपको अच्छी तरह से समझ में आया होगा how we represent flux. Okay, and the speed is a bit fast because many times you have already studied this, and you can also study it from the Dave J. Griffith as well. Okay, so Dave J. Griffith का जो text है ना बेटा, वो अच्छी तरह से पढ़ना. Okay, अच्छी तरह से. Okay, next we have this. So here we are at the flux. Now the most important equations are these two. Number one equation is that you want to calculate flux, it will be given by this: I is equal to integration of E dot dA, like this. I is equal to integration of E dot dA, or you can write it like this as well: flux is equal to integration, like this as well. You can write it like this as well: flux is equal to what? That's equal to integration of E dot dA. Okay, so the equation number first is true for the closed surface, and the equation number second is true for the open surface. So this one is true for closed surface. This one is true for closed surface, right? And this one is true for the open surface. This one is true for open surface. Okay, perfect. So this is true for the open surface, right? Okay. अब देख लो बेटा. Okay, so let's do a couple of examples here. Okay, let's do a couple of examples here on the flux. Okay, तो इसी तरह से ध्यान रखना बेटा. So here I'm going to write down examples on flux, electrostatic flux. Examples on electric flux. Examples on electric flux. Examples on electric flux. Okay, so we'll be starting with the simplest example. That simplest example number 1 is like this. The simple practice example. Okay, so it's like this. For example, here we have coordinate system is given to us. Let's suppose that this x-axis, ये मान लेते हैं this y-axis, and this our z-axis. Fine. Okay. Now electrostatic field is given to you. Electrostatic field is like this. It's equal to E naught multiplied by I K, which means that electrostatic field is constant, which is E naught, and it is directed along the x-axis, so it's directed along this direction. Fine. Along this direction, there's an electrostatic field which is equal to what? That's equal to E naught multiplied by I K. Okay. Now here in the YZ plane, there's a rectangular lamina like this. There's a rectangular lamina like this. Okay. Its dimensions are, its length is equal to A and breadth is equal to B. Dimensions are A and B. Dimensions are A and B. Okay. Now the question is like this: calculate the flux through the surface. So you are supposed to calculate what is the flux through the surface. You have to calculate flux through the surface. Okay. So let's calculate the flux. First of all, step number first is that define the area vector. Yeah. So area vector will be obviously in this direction. Okay. So this area vector, it's always perpendicular to the plane of the surface. So it will be in turn equal to A multiplied by B multiplied by I cap, isn't it? Its area is called AB, and it is directed along the x-axis. So I cap here. Okay. Or you can write down here x cap as well. Purely your choice. Right? अब देख लो बेटा. So here we are. Now we can calculate the flux. So here I'm writing it. The flux is equal to, now is the dot product of the area vector and electrostatic field E dot A. Fine. Now electrostatic field is in turn equal, that's equal to E naught multiplied by I K dot area vector is equal to what? That's equal to AB multiplied by I K. AB multiplied by I can, then dot product of I dot I is simply 1, so it's simply equal to E naught multiplied by AB. How much it is? E naught multiplied by. You cannot expect this question in the net examination or the test examination, but this is just a practice example. Okay. Next example, okay. Example number 2. Let's do another example. That's example number 2. Fine. Example number 2. Example number 2 is something like this. Suppose that here we have a uniform electric field. Now, these types of questions are asked in the net examination. So it's like this. This is a uniform electric field. Now, a closed surface is placed in a region of uniform electric field. Like this, for example, suppose that we'll take closed surface. Let's take the closed surface like this. It's a cylindrical surface. Like this, okay? A closed cylinder is here. Closed cylinder height. Okay, now these are the electrical lines. Like height. Okay, its height is given to you, that's equal to h. Its height is given, that's equal to h. And its radius is given, that's equal to r. Radius given, that's equal to r. Now the question is like this. Calculate A part flux entering the surface. Number 1 is that A part is that you will have to calculate flux entering the surface. Flux entering the surface. Flux entering the closed surface. B part is that you will have to calculate the flux leaving the surface. B part is that you are supposed to calculate flux leaving the surface. Flux leaving the surface. And C part is that you are supposed to calculate net flux through the surface. But the net flux that's passing through the surface. Okay. Fine. Okay, great. Perfect. Now what you'll do is that you will use the sign convention, and the sign convention is like this. The flux entering is always taken as negative and the flux leaving is taken as positive, and there's a good reason for that. There's a good reason for that. The reason is like this. Okay, so what I will do, what I will write is this, that the flux E implies entering is taken as negative. Is taken as negative, and the flux leaving is taken as positive. Is taken as positive. Why? There's a reason. The reason is like this. So it's, for example, here we have this uniform electric field. Now, in this uniform electric field, what we'll do is that we'll place a spherical surface like this. Like this is placed. Fine. Okay. Now, the area vector at this point will be in this direction. That will be in this direction. Along this direction, there will be dA vector. By dA vector is this elemental area. Fine. And then at this point, the dA vector will be in this direction. For a closed surface, the area vector is always directed outwards. Okay. So this is dA vector. Fine. Now, electric field, agar aap dekh loge beta, so electric field will be in this direction. So at this point, what is the angle here? The angle here, that's equal to 0 degree. So the flux is leaving. Angle theta is equal to 0 degree. Agar aap phi nikaloge beta, that will be equal to positive. So let us simply equal E multiplied by dA, and it will be positive, isn't it? And if you want to calculate flux at this point, electrostatic field is in this direction. What is the angle between the electrostatic field and the dA vector? Obviously, the theta here, that's equal to 180 degree. If theta 180 hoga, so cos 180 will be equal to what? That will be equal to minus 1. So that means the flux here will be equal to minus times E multiplied by dA. Okay, so point number 1. Point number 1 is that the flux entering is taken as positive, sorry, negative, and the flux leaving is taken as positive. Number 1. Number 2 is that if there's a closed surface and it is placed in a region of electric field, region of uniform electric field, and in that period here, suppose that there is no charge enclosed by this, by the closed surface, the net flux will be surely equal to 0. Net flux will be equal to 0 if there is no charge enclosed. Simply the reason is that the flux, suppose that there are 10 field lines that are entering the closed surface, so obviously 10 field lines will be leaving the closed surface. Hence the net flux will be equal to 0. Net flux tab hoga non-zero. Number 1, when it's placed in a region of non-uniform electric field. Number 1. Number 2 is that when some non-zero charge particle is placed inside. Okay. In those two cases, the net flux can be not equal to 0. But in general, if for example there's uniform electric field and a closed surface placed without enclosing any charge, then the net flux will be equal to 0. Dekh lo beta. Now we'll be doing the examples here. Okay. Now we are supposed to do example number 2. और एक important point यहाँ आपको याद रखना है बेटा. That's like this. If you want to calculate flux, whether it is flux entering or flux leaving, you want to calculate flux for a closed surface. For a uniform surface, it will be like this. For a uniform electric field, flux will be equal to electrostatic field E. Electrostatic field E multiplied by area of projection. Multiplied by area of projection. But that area of projection is parallel to electrostatic field. Area of projection that is parallel to electrostatic field. अच्छी तरह से ध्यान रखना. What does that mean? We are actually supposed to calculate the flux entering in this series. For example, this is a uniform electric field, and here we have what? This is cylindrical surface. This is cylindrical surface. Right? Okay. अब देख लो बेटा इसका area of projection क्या होगा in the direction of field. So this will be the electric line. Okay, so these are electric line. Okay, what will be the area of projection? Area of projection, what does that mean? Its radius is r, and this height is equal to h, like this. So this is the jugaad to do this problem. Okay. Without you can safely skip the integration and do this problem directly. अच्छी तरह से ध्यान रखना बेटा. So what does mean area of projection? Area of projection implies that, for example, अगर आप यहाँ से light डाल रहे हो, तो यहाँ इसकी projection बनेगी. So its projection will be 2-dimensional. It's a 3-dimensional figure, but the projection will be 2-dimensional, and the 2-dimensional will be simply a rectangle. इसकी जो projection होगी, that will be a rectangle, and that will be something like this. That will be something like this. The rectangular region, that will be something like this. Okay, so it will be like this. So I hope beta is the area of projection. So number one like this, then like this, then like this. Okay, so this will be the area of projection. Fine. Okay, and the area of projection will be simply a rectangle whose length, this breadth, will be equal to twice r the diameter of this cylinder, and whose height will be simply equal to h. Okay, now in this very case, if you want to calculate flux entry, अच्छी तरह से ध्यान रखना. Okay, so flux entry. Okay, so flux entry will be negative. It will be simply equal to minus electrostatic field multiplied by area of projection, and area of projection is equal to what? That's called length into breadth, so which is equal to 2r into h. So यहाँ आएगा बेटा 2r multiplied by h. 2r multiplied by h. So this is the flux entry. Fine. And if you want to calculate flux leaving, safely you can calculate that as well. That will be simply plus E multiplied by 2RH, the area of projection. Okay, and flux entering is taken as negative, flux leaving is taken as positive. Fine. Okay, then if you want to calculate the net flux, is obviously equal to 0. The net flux will be how much? That will be equal to 0 as expected, because there is no charge which is enclosed inside. Okay, so that's why the net flux will be equal to 0, isn't it? So we are done with this, I think. Okay, we have calculated what the flux entering, what the flux leaving, and then we have calculated the net flux as well. Okay, we'll be doing an example, and that has been asked in the net examination, so we'll be doing example on that later on. But let's do another example. Example number 3 is something like this. Example number 3, that's like this. Suppose that again here we have a uniform electric field. Fine, so this is a uniform electric field. Now inside this uniform electric field, a cone is placed like this. There is a closed surface which is cone, it's placed, and this radius is given that is equal to r. Its radius दिया गया है बेटा, that is equal to r, and the height of this cone is given that is equal to h. Now the question is calculate flux entry, flux leaving, and net flux. So you are supposed to calculate flux entry, flux leaving, and net flux passing through the surface. Fine. So again, first of all, what you have to do is that you will have to see what's the projection area. So iska projection area. Suppose that what you will do is this: you will place a lamp here, you will place a torch here, and then here is the screen. So on that screen, the area will be simply a triangular area. It will be a triangular area like this. So that means area of projection will be something like this. Iska area of projection ये होगा. ये इसका area of projection होगा, whose base will be equal to the diameter of this, so that's equal to twice r, and whose height will be simply equal to height of cone, so this is equal to h. अब इसका area क्या है? What's the area of this? Area is simply equal to 1/2 base into perpendicular, तो वो आएगा 2r multiplied by h. So 2 and 2 is going to cancel, so the area will be simply equal to r multiplied by h. Fine. You have calculated the area. Now safely you can calculate the flux entry, the flux leaving, and the net flux. So flux entry you want to calculate, that will be equal to minus times E multiplied by the area of projection, R multiplied by H. You want to calculate flux leaving, that will be equal to plus E multiplied by R into H. And then you want to calculate net flux, obviously that will be equal to 0. So net flux कितना होगा? That will be equal to 0. So यहाँ आप लिख सकते हैं net flux will be equal to 0 in this case. Okay, so I'm sure example number 3 is also clear to you. Now let me give some examples as home assignment for you. Okay, it is like this. So here we have example number 4, and it's kept as home assignment for you. It's like this. So same procedure is exactly same. Here we have this uniform electric field, and in this uniform electric field, what we'll place is this: we'll place a cone like this. I say cone place करेंगे बेटा. Its radius, its height is given, that's equal to h, and its radius is equal to r. So you are supposed to calculate flux entering and flux leaving. Electrostatic field is given, that's equal to E. Number 1. Number 2, for example, there is a cylinder which is placed like this. Its height is equal to h, and its radius is equal to r. Again, same question is here. You are supposed to calculate what the flux entering and flux leaving. Okay, fine. So number 1, number 2, and then there's a hemisphere like this. For example, a hemisphere is like this. So this is a hemisphere whose radius is equal to r, and you are supposed to calculate. Right? So step number 1 is that try to calculate the area of projection. Okay? जब मैं यहाँ से लाइट डालूंगा, तो इसका जो area of projection होगा, that will be simply circle. And here the image will be here, the projection here, that will be also circle, and here it will be semicircle. So that means इसका area जो है ना बेटा, area that is simply equal to circle, which is called pi r square. And the area of this, that will be also equal to area of projection, that is equal to pi r square, or cross section area, that will be equal to pi r square. And the area of projection of this, if you place a bowl in front of a bulb, the image formed on the wall will be simply a semicircle. Okay, so that will be equal to pi r square by 2. Pi r square by 2. Once you are done with this, so basically the problem boils down to calculate the area, the projection area. So you must be able to identify which projection area will be there, and accordingly calculate area. Once you are done with the area, the problem is almost done. Okay. Then you can calculate here flux entering, that will be simply equal to minus times E multiplied by r square. Accordingly, you can calculate flux leaving, that will be false. Net flux will be 0 in all the cases, because there is no charged particle which is placed inside. Number 1. Number 2 is that the electrostatic field is constant. If there are 10 field lines which are entering, the 10 field lines must be leaving as well. Okay, so I'm sure ये तीनों example आपको अच्छी तरह से समझ में आई होंगी. Okay, great, perfect. Okay, so we are let's do another example. In if there is a non-uniform electric field, we'll do one example on that. Okay, let's do one example on that pattern. So अच्छी तरह से ध्यान रखना. So it's something like this. So here I will write down. We are supposed to calculate example number 5 is that we are supposed to calculate the flux of a closed surface when the electrostatic field is non-uniform. So here I'm going to write it. There's non-uniform electric field. Non-uniform electric field. There's a non-uniform electric field. Fine. Okay. So it's like this. Suppose that here we have electric field is given like this. Electrostatic field is equal to E naught multiplied by X multiplied by I Km. So what does it mean? It means that number one, it varies along the X direction and it is directed along the X axis. Okay. Fine. So it's like this. So it's like this. This cube is given to you. Then it's like this. This is the coordinate system, and here we have a cube is given to you like this. A cube is given here. So ये हमारे पास है cube. Okay. Its side is equal to A. So then dimensions are given, different dimensions are given like this. For example, here we have this X axis. This is Y axis. This is Z axis. Right? This is given that X equal to A. This is given X equal to A, and this is given X equal to twice A. Okay, fine. And the length and breadth that is equal to A. Okay, so here it's A and here it's A as well. So this will be also equal. This dimension also equal to A. Length, breadth, height that's equal to A. Right? Now what you're supposed to calculate is this. You'll have to calculate what is the net flux through this. Okay, so you'll have to calculate what is the flux. Calculate flux through this. Flux through the cube. Calculate flux through the cube. You are supposed to calculate flux through the cube. Right? Okay. So what I will do is this. अच्छी तरह से ध्यान रखना. The electrostatic field is directed along the x-axis. That means the electrostatic field is directed along this direction. So this is the direction of the electrostatic field. It is variable indeed. Variable implies that it varies only along the x-axis. Fine. Okay. So at origin, electrostatic field will be equal to 0 because x is equal to 0. At this point, electrostatic field will be equal to E naught multiplied by A because x is equal to A. And at this point, electrostatic field will be equal to E naught multiplied by twice E. Fine. Okay. Now that means now the flux through the four lateral surfaces. There are how many surfaces? There are how many faces of this cube? There are 6 faces of the cube. Through 4 lateral surfaces. Through the lateral surface, the flux will be simply equal to 0. That means flux will be non-zero through this surface and through this surface. And here the flux will be entering, and here the flux will be leaving. So obviously this flux is taken as negative, and this flux is taken as positive, isn't it? So that's what I'm going to write here. So I will write down like this. Let's calculate first of all the flux entering. So flux entering will be equal to minus E multiplied by electrostatic field at this point. At what point electrostatic field? At x equal to A. Electrostatic field at x equal to A multiplied with the area. Multiplied by A. Fine. Now what is the electrostatic field? So here electrostatic field. So obviously area vector will be in this direction. Okay. Sorry. Electrostatic field will be in this direction, but the area vector will be in the outward direction. So ये area vector होगा. So what is the angle between the two? The angle is 180. So dot product will be negative. Fine. So it will be like this. Now what is the electrostatic field? तो यहाँ electrostatic field आएगा बेटा minus E naught multiplied by A because x is equal to A. और इस A के बदले क्या लिखेंगे बेटा? यहाँ लिखेंगे A square. It is the area of the side of cube that's called A square. So electrostatic flux entering will be equal to minus E naught multiplied by A cube. This is the flux entering. And then if you want to calculate flux leaving safely, you can calculate that will be obviously equal to what? That will be equal to plus E multiplied by electrostatic field. You have to calculate electrostatic field at this point. So यहाँ x का value क्या है बेटा? X is equal to 2A. So here I am going to write it. X at x equal to 2A multiplied the area A. Fine. So electrostatic field will be equal. This will be here E naught multiplied by x is equal to 2A. So here I am going to write it 2A, and here I am going to write down the area of side of a cube that's called A square. So ये electrostatic field positive आएगा plus 2 E naught multiplied by A cube. Now you will have to calculate net flux. So obviously net flux will be equal to simply the summation of the flux entering and flux leaving, isn't it? Now flux entering is taken as negative, so it is equal to minus E naught multiplied by A cube, and flux leaving is positive, so plus 2 E naught multiplied by A cube. So the net flux that is passing through the cube will be obviously equal to E naught multiplied by A cube. ठीक है बेटा? So I am sure ये example आपको अच्छी तरह से समझ में आई होगी. Okay? Okay? ठीक? So we have calculated the flux entering as well as flux leaving as well as the net flux that is passing through the surface. Okay? Great, perfect. Okay, अब देख लो बेटा next example. So non-uniform electric field हो गया, and uniform electric field we are done with that as well. Okay. So let's do an example that has been. Okay, perfect. So we are done with this. Okay, now next is this. Next dekh lo beta, that is this electric flux for a closed surface. This statement of the Gauss law. Now what is Gauss law? Gauss law is simply like this, that the electric flux for a closed surface is directly proportional to the charge that's enclosed by the surface. That means it's like this, something like this, that the flux for a closed surface, which is in turn given by this integration of E dot dA, integration of E dot dA is directly proportional to Q enclosed. By Q enclosed what? The charge enclosed by a closed surface. That's obvious. More that it's obvious. It's like this. Simply it's like this. For example, here we have this a closed surface, and inside this closed surface a charged particle is placed. Fine. Okay. Now you know that the number of field lines that are drawn from a closed surface. You know that the number of field lines that are drawn from a closed surface is directly proportional to charge, isn't it? Okay. So more the charge, more the number of field lines we'll have to draw. More the number of field lines we'll have to draw implies more is the electrostatic flux that is passing through the closed surface. Obvious. Fine. So statement of Gauss law is simply like this, that the electrostatic flux for a closed surface directly proportional to charge enclosed. Okay. So next what I will do is this. Okay. So next I can write it like this. Okay. So this is the flux. So next I will write like this: the flux for a closed surface is equal to integration of E dot dA, and that's equal to K multiplied by Q enclosed. Fine. So it will be equal to K multiplied by Q enclosed. Okay. Now this K is a constant of proportionality. Fine. Constant of proportionality, whose value depends on two factors. It's a constant of proportionality whose value depends on two factors. Number one, the system of units we are using, number one, and number second, the medium in which the charged particle is placed. Okay. So accordingly, K will have four different units. Okay, four different values like this. K is equal to 1 by epsilon naught. It's equal to 1 by epsilon naught when the system of units we take is SI, and there is vacuum in which the charged particle is placed. K is equal to 1 by simply 1 by epsilon naught. Okay. So here we are 1 by epsilon naught. Then K is also equal to 1 by epsilon naught multiplied by epsilon naught. This is true when the system of units is SI and there is some medium in which the charged particle is placed. And obviously, when a charged particle is placed inside a medium, what will happen? The flux is that it is going to decrease by epsilon naught times or by dielectric this K times by K the dielectric constant. Okay, so this is here K, that's equal to 1 by epsilon naught in SI oblique vacuum, or it's equal to 1 by epsilon naught multiplied by epsilon, or then we use SI oblique medium. The next is that K value is also equal to this. K value is equal to simply 4 pi. It's equal to 4 pi when the system of units used is CGS, and there is vacuum which is separating the two charged particles. Fine. Then it's also equal to, its value is also equal to 4 pi divided by capital K. It is also equal to 4 pi divided by capital K when the system of units is CGS and any medium is there in which the charged particle is placed, and K is the dielectric constant of that medium. Fine. Okay. Then accordingly we have how many equations for this? Accordingly we have four different equations for the Gauss law. They are like this. So equation number one will be like this: phi is equal to, it is simply equal to Q enclosed divided by epsilon naught. Number one equation. Number second equation is like this: Q enclosed divided by epsilon naught multiplied by epsilon naught. This equation is true when there is what? Vacuum, and when there is SI system. SI system we are using, and there is vacuum in which the charged particle is placed. And this is true when the system of units is used as SI and there is some material medium in which the charged particle is placed. Okay, so this is flux pi. Then two more equations, they will be like this, that flux will be equal to 4 pi, simply 4 pi. It will be equal to what? 4 pi multiplied by Q enclosed, 4 pi multiplied by Q enclosed when the system of units is what? That is CGS. And when the system of units is CGS and there is some what? There is vacuum which is in which the charged particle is placed. Then this flux will be also equal to, we can also write it like this: 4 pi by capital K into Q enclosed, where this is the flux when the system of units is used as CGS and the medium is there is some material medium other than the vacuum in which the charged particle is placed. Fine. Okay. अब ये equations wire from these four different constants Km. Actually, you know that there are four different equations for the Coulomb's law as well, if you remember that. So electrostatic field, the point charge is simply equal to K into Q divided by R square, but that K can be equal to 1 by 4 pi epsilon naught. That can be equal to 1 by 4 pi epsilon naught into epsilon R. That can be even equal to what? That can be even equal to that will be equal to 1 by capital K, or that can even be equal to 1. Isn't it? That accordingly there will be four different equations from here. Okay, ठीक है ना बेटा? Okay, so what the most important equation here is this for the Gauss law, that's simply like this: the flux to a closed surface is given by this integration of E dot dA, and that's in turn equal to Q, and that is phi m rather will be equal to phi naught divided by epsilon or divided by capital K. Like this it is. It can be written like this: epsilon phi naught divided by epsilon or it will be equal to phi naught divided by capital K. What does that mean? That simply means that if there's a charged particle like this and this is surface, fine. Okay, this is surface. Okay, now this is a charged particle. Now some field lines. Suppose that there are 100 field lines you are passing through this. Okay, there are 100 field lines you are passing through this. Next, what you will do is this: you will place it inside the medium. Okay, what you will do is this: you will place a medium somewhere here in which the charged particle is placed and whose dielectric constant is 10. So what does that 10 mean? That 10 means that the number of field lines will now decrease by 10 times. ठीक है ना बेटा? पहले electric field lines थी, for example 100. Now the electric field lines will be, the number of electric field lines will be now equal to 100 divided by 10, which is equal to 10. So that means the flux as well as the electrostatic field due to the capital Q that reduces when this capital Q is placed in a region of when it's placed in a medium. Okay, when it's placed in a medium. So both the flux as well as the electrostatic field due to the point charge will decrease when the point charge is placed in a material medium. Okay, so I think this is now clear to you how we define this Gauss law. It's simply like this integration of E dot dA, and then you can show the proof here as well. Okay, so a small proof here as well. Small proof, simply it's like this. Okay, so there's a charged particle Q, and here we have this a closed surface, and we are supposed to calculate the flux through this, and it must be equal to Q divided by epsilon naught, isn't it? So let's calculate the flux. Flux will be simply equal to integration of E dot dA. Okay, now dA is what? That is the area element. So here we can write down the area element like this. Now this is the area element here, so it is directed in the outward direction, so this is dA, isn't it? Then what you can write is this electrostatic field here will be equal to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught multiplied by Q divided by R square multiplied by R cap. Why R cap? Because it is directed radially outwards. And then you can write down the dA vector as well. It is simply equal to its magnitude is dA multiplied by R cap, because it is even also directed radially outward. Okay, so let's calculate the flux now. Let's calculate the flux. Okay, so we can calculate safely the flux. So flux will be here, phi will be in turn equal to what? Flux will be equal to, so flux will be equal to what? That will be equal to E dot dA. So it's equal to integration of simply E multiplied by dA. Okay, so simply it's like this: E multiplied by dA, because R cap dot R cap will be equal to 1. Then what I can do is here is this: the electrostatic field is constant everywhere, so pull it out, integration of dA. Fine. This electrostatic field can be replaced by 1 by 4 pi epsilon naught multiplied by Q divided by R square. Then here it's integration of dA, that's in turn equal to surface area of the sphere 4 pi R square. This 4 pi R square is going to cancel with 4 pi R square, तो यहाँ क्या बचेगा? Q divided by epsilon naught. So this is the net flux which is passing through the surface. Okay, which is passing through the closed surface. Okay, and this implies that the flux is given by this integration of E dot dA, which is in turn equal to Q divided by epsilon naught. Okay, so this proof I have copy pasted this simply from the David J. Griffith. आप देख लो बेटा, David J. Griffith पर है इसका proof. Okay, so you can see from here as well. Okay, तो इसका proof उतना important हमारे लिए नहीं है बेटा. What's important is that the final expression is highly important for this. Okay, fine. अब देख लो बेटा, next is this Gauss law in the differential form, and then questions can be asked from both Gauss law in the integral form as well as the Gauss law in the differential form. This is the equation. This equation is written as what? It is the Gauss law in the integral form. Okay, so let me derive the Gauss law in differential form from the integral form. Okay, तो अच्छी तरह से यहाँ ध्यान रखना बेटा. Okay, we'll derive it out quickly. Though it's not a prime importance, the derivation is not a prime importance as far as the competitive exams are concerned. Okay, तो अच्छी तरह से ध्यान रखना बेटा. So we have what? First of all, I will write down like this: Gauss law in integral form. Let me write down Gauss law in integral form. Okay, so Gauss law in integral form can be written like this. It can be written like this: simply the flux to a closed surface is equal to integration of E dot dA. Integration of E dot dA, that's equal to Q enclosed, simply Q divided by epsilon naught. Fine. Then here what I will use is this: I will use the Gauss divergence theorem. Gauss divergence theorem. I will use the Gauss divergence theorem. पढ़ा होगा आपने BSc में. Okay, Gauss divergence theorem. Gauss divergence theorem. तो देख लो बेटा, अच्छी तरह से ध्यान रखना बेटा. Gauss divergence theorem is simply like this. It's like this. It is used to convert the surface integral into the volume integral. It's like this: that integration of, for example, any vector. Suppose that vector is something like, let's take the vector A. integration of vector A, okay, or for example let's take any other vector like vector V. Let's take the vector V. It's not necessarily it's vector A, it can be like this as well. It's like this vector V dot dA. Integration of vector V dot dA surface integral will be equal to what? It will be equal to volume integral of the divergence of this nebula dot V, volume integral of this, okay. Then d tau here, where d tau or dV, it's what it is, it's the volume element here, okay. So what I can do here is this. So I can, what I can write here is this. I can use the this Gauss divergence theorem, okay. So using Gauss divergence theorem, we have just the integration of E dot dA. E dot dA is equal to Q enclosed by epsilon naught. Q enclosed by epsilon naught. Here it's like this. This is the Gauss divergence theorem, and here for the closed surface, V dot dA is equal to nebula dot V. This is the divergence of the vector V and its volume integral. Fine. Then we can replace this by this volume integral of nebula dot E d tau. You can write like this simply using a Gauss divergence theorem. This is equal to 1 by epsilon naught, and this here charge, it can be written like this in terms of charge density. It's equal to rho into d tau. Rho into d tau. Now simply it becomes that it becomes nebula dot E. This equation reduced to this equation, nebula dot E is equal to rho divided by epsilon naught. Rho divided by epsilon naught. So this is Maxwell's first equation. Number one is Maxwell's first equation and Gauss law and the divergence. So this is Gauss law number one, and number second is also called as Maxwell's first equation. Maxwell's first equation. Okay. So here I am going to summarize both the equations. So equation number one, जो आपके पास है बेटा, there is a Gauss law in the integral form that's like this. Electrostatic flux for closed surface is given by this integration of E dot dA. Integration of E dot dA, and that's in turn equal to Q enclosed divided by epsilon naught. And number second is this. Number second, the flux, the closed surface is given by this, that's equal to nebula dot E. That's also given by nebula dot E, and that's in turn equal to what? Rho enclosed divided by epsilon naught. Rho enclosed divided by epsilon naught. Okay, we'll be doing the examples on the first equation as well as on the equation number second as well. Okay, so both are the Gauss law. First equation is called as the Gauss law in the integral form, and second equation is called as the Gauss law in the differential form. So surely we'll be doing the examples on both. That's on this and on this as well. Okay. So कल जो हम examples करने जाना बेटा, so we'll be restricting ourselves to the net and just NT4. Okay, so we'll be doing some examples on that. Okay, so there are some important points. Okay, you read these important points yourself. Okay, then we'll be doing some examples, and then we have examples like this. This is different example. Okay, then here we have this different example is actually copy pasted from, simply this example is copy pasted from this Dave J. Griffith. Okay, so let me keep a home assignment for you rather. I will keep a home assignment for you from the David J. Griffith. Home assignment for you from David J. Griffith. Okay, so इसमें कौन सा है? So here I am going to write it. So here I will write down problem number. Problem number 2.4 to 2.8. Spherical surface नहीं करेंगे. From problem number 2.4, 2.5 and 2.6. These three examples are elected as home assignment, and it is addition. You must have a new edition of this.